Hello, welcome back to ICCP 2020. We're going to continue on with technical session 2B. My name is Surain Jayasuriya, and I'm be your session chair today. Today we have four great papers that involve novel sensors and illumination devices and have a hardware component. Just a reminder, as the videos are playing, you can write your questions into the live chat, and I will be monitoring that to ask the authors after the talks are finished. The first talk is called SweepCam, Depth-Aware Lensless Imaging Using Programmable Masks, and the authors are Yi Hua, Shigeki Nakamura, Salman Asif, and Ashwin Sankanarayan. And we'll start with the first talk.
We present depth-aware lensless imaging using programmable masks. There have been numerous designs for lensless imaging that differ primarily in the choice of modulating element used to replace the lens. An amplitude mask is used in FlatCam and FlatScope. Thin face masks are used in the form of a microlens array in Tombow, spiral gratings in PicoCam, diffuser in DiffuserCam, and 3D printed contour masks in face mask-based FlatCam. All of these designs aim to produce an image without requiring a lens, and its associated bulk and standoff distances. Reconstructing depth-varying scenes, such as one shown here, is challenging for lensless imagers. As a consequence, their reconstructions have significant artifacts. This paper reconstructs depth-varying scenes from lensless measurements by introducing programmable masks. The proposed imager, called SweepCam, can resolve scenes with large depth variations and achieves this with a lightweight, computationally efficient algorithm. First, let's understand why lensless imaging with depth is hard. Consider an amplitude mask lensless camera. The measurements of a point light source are shadows of the amplitude mask. When the points are at the same depth, the point spread functions, or PSFs, are translated copies of each other. Thus, for a scene consisting of a single depth, the measurements can be modeled as its texture convolved with its PSF. And simple deconvolution is often sufficient to reconstruct the scene. When points are on different depths, however, the PSFs become depth-dependent. As a consequence, reconstruction becomes difficult as we need to solve for both the depth and the brightness of the point sources. Consider inserting another plane at a further away depth. Here is a new imaging setup. Now, for this scene made of two planes, if we take the measurements from the sensor and deconvolve it with a PSF from near plane, it results in poor reconstruction with artifacts. So why does the reconstruction of a multi-depth scene have artifacts? Now, the measurement is a sum of two components. Each component is the texture at the depth convolved with the PSF. As shown before, the PSF at different depths are the mask patterns scaled by different amount. When the scene only contained the near plane, deconvolving the measurement with the near plane's PSF is sufficient to recover the scene, as deconvolving the PSF with itself yields to a delta function. We can recover the scene at the near plane. However, deconvolving with a mismatched PSF results in artifacts. Ultimately, treating the scene as it only lies on single depth results in poor reconstruction with artifacts. And the artifacts are present in reconstruction of all depth planes. Currently, there are two broad approaches for reconstructing depth-varying scenes. The first one models the scene with a texture map and a depth map. The number of unknowns is approximately twice that of the measurements, but it is a highly nonlinear inverse problem. The second approach is to model the scene as a volumetric texture or intensity function. For example, this scene would decompose into textures onto multiple depths. Plane 1, Plane 2, Plane 3, Plane 4. There needs to be enough number of depth planes in the volume to correctly model a surface with continuous depth variation. As a result, the number of unknowns becomes much larger than the number of obtained measurements, and this reconstruction becomes a severely underdetermined problem. Since both of those problems are underdetermined, can we obtain more measurements with different mask patterns and make the reconstruction problem well-determined? Furthermore, can we isolate a particular depth and only reconstruct that? To address the underdetermined reconstruction problem, we introduce programmable masks into lensless imagers to obtain more measurements. If we select the right mask pattern, we have a well-conditioned system with a large number of both unknowns and measurements. The key contribution of this work is using programmable masks for well-conditioned and depth-aware reconstruction. We show that translated masks can be used to bring a computational focusing operator into lensless imager so that we can reduce the size of the reconstruction problem to a single depth plane and dramatically improve reconstruction speed. Let me illustrate the focusing operator with a simple mask, a pinhole. The effective focusing is very similar to that from a lens. As we translate the mask, we obtain multiple measurements. Note, scene at different depths move with different disparity. Let's focus on the near plane. First, we calculate its disparity from depth of the near plane. Then, we can shift the measurements accordingly and sum the measurements to focus on the near plane. Note, in the case of a pinhole, the in-focus plane measurement is the texture of that plane, and the out-of-focus plane is the plane's texture convolved with a comp function. We can obtain the same for the far plane by simply choosing a different disparity. The same focusing operator can be applied to lensless measurements with more light-efficient masks. We can still focus to emphasize measurements from the near plane. And similarly, that from the far plane. Note, in the focus near image, the red bolt in the near plane is more visible than the in-focus far image. The focusing operator suppresses contribution from other depths. So how does focusing with SweepCam measurements suppress contribution from other depths? When there is no focusing, the raw measurement is sum of two depth planes convolved with their respective PSFs. Let's see what changes in the focused measurement. As we saw in the pinhole case, the in-focus plane, the near plane, does not change. But the out-of-focus plane, the far plane, is additionally convolved with a comp function. Now, when the focused PSF is deconvolved with the round PSF, the high-frequency artifacts are suppressed by the comp function. Therefore, the artifacts from the far plane are suppressed. So, this is reconstruction for near plane and for far plane. To evaluate the proposed lensless imager with programmable mask, we'll build a hardware prototype. The setup is quite simple, consisting of a programmable amplitude mask and a sensor. We use an RGB sensor with 5 micron pixel pitch. The programmable mask is implemented with an LCOS with pixel pitch of 36 micrometers, sandwiched between a pair of cross-polarizers. The bulkiest part of this setup is a precision rotation stage for mounting one of the polarizers, so that we can adjust the alignment of two polarizers to maximize the contrast ratio of the programmable mask. In this scene, a plane with flower patterns is placed at an angle in front of the imager. The focal stacks shown here are obtained by reconstructing for different depths. On the left, we show reconstruction results from 338 measurements with a static mask, and on the right, we show reconstruction from the same number of measurements obtained with translated masks. The high-frequency artifacts for the static mask results are caused by interference across depth, and they're removed on the SweepCam results due to the focusing operator. We can estimate depth of the scene by assigning each pixel the depth at which it has the highest local contrast. Pixels which have very low contrast throughout the stack are dropped. As shown, removing the artifacts resulted in better depth estimation in the textured regions. We also compared to the previously mentioned approach that jointly solves for texture and depth of each point. Here is another scene of succulent plant. Note the white bumps on the plant comes into and fades out of focus as the focus sweeps back and forth. In summary, the proposed method can handle continuous depth scenes without relying on sparsity prior. Consequently, the reconstruction is simple and fast, and we can generate a dense focal stack of the scene. And finally, we can estimate depth from the dense focal stack. However, these advantages come with certain limitations, in that we do not model occlusion, specularity, or sensor's angular response. For example, the specular pearl produces artifacts in this reconstruction. Additionally, SweepCam requires capturing multiple measurements, and hence a reduced time resolution. In conclusion, this work addresses the challenges of imaging depth variancing with lensless imagers. We hope this will allow for more practical applications for lensless imagers. For more details, please refer to our paper. Thanks for watching.
Great. So we have Yi joining us to answer some questions. So please write your questions along that, and I'll get started with some questions. So George Chen says, very cool work. If the scene is dynamic, would the motion parallax model still work?
So SweepCam takes multiple frames, so it has all the problems with multi-frame approaches. One example is if the scene is dynamic, this model would not hold. We are thinking about alternative approaches where you can do this in a single exposure or a very short exposure time. But for now, it does not hold. The motion parallax model does not work.
Okay, great. Takuya Funatomi says, is there a resolution of focusing along depth?
Yes, so the ability to distinguish depth is different. And in fact, in this model, the resolution in diopters, which is 1 over depth, is proportional to the, it depends on 2 things affect it. One is the distance between the sensor and the measurements, the sensor and the mask, and also the pixel size, the ratio of the pixel sizes. So this resolution along the depth, it is linear in diopter space.
Okay, great. I'll jump to Chang Fu. It said it looks like the out of focus regions, they have some like ringing artifacts. Do you know what might be plausible causes for those ringing artifacts?
So eventually this is at least the way we've approached it, the results we show are results of basically a series of convolutions. And as we presented in the talk, depending on how you translate the mask, the pattern you translate the mask, you will get different kernels and different inverse kernels. So the out of focus regions will take on the shape of the pattern that you shift your mask to.
Okay, and Rahul Kove says, what is the range of motion needed for the mask?
What is the range of motion?
I'm interpreting he means like in the parallax. What is the range of motion? So I'm not sure. Maybe he can write down to thing. I'll ask a follow-up question though. So related to you talked a little bit about the limitations of the angular. Like you're not taking into account the angular kind of representation, because in some sense you could look at this like a light field representation. If you were to go in that way, how would the modeling change?
How would the modeling change? So right now we have a very simple model where we model scene points as points that uniformly distribute light in all directions. So basically, in this sense, we have very little angular resolution, and that allows us to get a very fast reconstruction algorithm. However, if we were to consider a more complicated model where we have angular resolution, or for example, the scene points emit a different amount of light in different angles, then I think the problem becomes non-linear or very difficult to solve. And I would suggest a better approach is to use the optimization problem and do iterative updates on that. And I think for this work, we produce this fast approach, and this would be a very good initial starting point for the iterative optimization method.
Okay, great. Unfortunately, we have to move on. So Yi will be around to answer the questions in the chat. And you can always, we'll keep the chat on after all the talks to answer. So moving on, we're going to the next talk is FoveaCam, a MEMS mirror-enabled foveating camera. The authors are Brevin Tillman, Ekta Jain, Sylvia Ferrari, and Sanjeev Kopal. We'll take it away.
Hi, I'm Brevin Tillman, and I'll be presenting FoveaCam, a MEMS mirror-enabled foveating camera. This work was done with Ekta Jain, Sylvia Ferrari, and Sanjeev Kopal. Various animal eyes selectively distribute resolution to important areas in their field of view. Selective imaging is crucial for efficiently expending neuronal resources only where it matters. The fovea in humans is a highly sensitive area in the retina that focuses resources to our direct line of sight. This lets us efficiently process our field of view only where we want and need. Birds have two fovea, one that operates similar to ours and another specifically for tracking slow-moving objects. In the ocean, cuttlefish leverage selective pupil contraction to see in dark areas. And mantis shrimp adaptively slide a polarization band to enhance contrast based on the polarization structure of the light traveling through the water. So we built a camera that can selectively distribute resolution to only important areas of the scene. And we do this by pointing a camera at a programmable MEMS mirror. And this MEMS mirror can tilt in a 2D plane and update at up to 120 kilohertz. So we leverage this to give simultaneous views of many regions of interest in a scene all at once. So here's a demonstration of the MEMS mirror tilting in a 2D plane. Here is a demonstration of FoveaCam. The top right is the raw footage of the MEMS mirror swiveling between the two red objects in the scene. And the bottom videos are the simultaneous extracted views from the raw footage. We designed the optics of the camera such that the MEMS mirror completely fills the field of view to prevent vignetting. And we use a MEMS mirror because they're quicker than motor-based galvo mirrors. Notice that we put more pixels onto the objects in the bottom videos, and this gives us a lower footprint compared to a very large resolution camera that would capture everything at once, like the helper camera. Here's the FoveaCam prototype. We use a 3.6 millimeter Miracle MEMS mirror, a 220 hertz FLIR machine vision camera equipped with a 35 millimeter lens. We use a Miracle MEMS mirror controller to update the position of the MEMS mirror and to keep the MEMS mirror and camera in sync. Our work is similar to catadioptric cameras, which focus on inserting mirrors into a camera's field of view. In the top left image, the authors insert two planar mirrors to simulate a stereo vision system. You only have as many viewpoints as mirrors in this case, so increasing viewpoints becomes expensive. In the bottom left image, the authors insert a curved mirror to greatly increase the camera's field of view to 360 degrees. However, you sacrifice angular resolution. In the right image, the authors build a dynamic projection mapping system, and this uses one-dimensional Gabo mirrors to track a single object. Our work differs from this in that we use a single mirror, and we develop a robust control algorithm to update the mirror to track multiple objects in the scene. Miracle MEMS mirrors come with a cover glass protecting the MEMS mirror. In the specific model we had, the cover glass reflected significant amounts of light in the visible ranges. In the left column, you can see this induces significant ghosting artifacts. So to overcome this, we insert a bandpass filter because within the 800 to 900 range, the cover glass reflected the least amount of light. It is known with Galvo and MEMS mirrors, they require a settling time before triggering the camera exposure if you want deblurred images. In our case, the settling time was 0.2 milliseconds, and this varied based on the resolution and number of measurements we sent at a time to the MEMS mirror. To begin explaining how we control our foveating camera, view this demonstration of what we would like the foveating camera to do. So the red square is the foveating camera's entire field of view, and we would like to distribute this square onto all regions of interest in the scene. We would like to distribute this resolution so fast such that it emulates multiple cameras looking at each region of interest. So in this specific example, it would be like two cameras, one looking at the bunny and one looking at the bird. Formally, let's model the bunny and bird as bivariate Gaussian distributions. QR is the current scan path the MEMS mirror takes between regions of interest, and F1 and F2 are the centers of the respective bivariate Gaussians. Finally, UR is the control vector for how we update QR. We define FT as the accumulation of both bivariate Gaussians, and then we define PD as the probability of detecting these bivariate Gaussians along the current MEMS mirror scan path. So PD is the probability of detecting a region of interest along the current MEMS mirror scan path. So we would like to maximize this probability with respect to the control vector. And the control vector is how QR, or the MEMS mirror scan path, is updated. We update this control vector by gradient descent. And I encourage you to read our supplementary material for how we derive with respect to the control vector. Once the control vector is optimized, we move the mirror along the new path. We can chain new regions of interest for moving the mirror to as many targets as we want. So our method is not limited to two bivariate Gaussians. We show the utility of placing higher angular resolution onto regions of interest with our camera by comparing it to a smartphone and eye tracking applications. To do this, we implement the eye tracking for everyone network, and this network was trained on smartphone images, and it outputs an XY coordinate of where the user was looking on their screen. Our data has a different color distribution and eye angle pronunciation than the data used to train the eye tracking for everyone network. Our data was taken at 3 meters, whereas the data used to train the eye tracking for everyone network was taken at 25 centimeters. To overcome this, we fine-tuned the network with a spread out training pattern. We also fine-tuned the network with iPhone data at 3 meters to respect the eye angle difference. Here's an example of data collection with the iPhone 6 and our FoveaCam. Here's a qualitative comparison between FoveaCam and the iPhone 6. The first row is one test set and the bottom row is another test set. The ground truth is in red, FoveaCam is in blue, and the iPhone 6 is in green. Here is a quantitative comparison between FoveaCam and the iPhone 6. The top table is one test set and the bottom table is another test set. After fine-tuning with 3 epochs, our camera outperforms the smartphone in every case. This supports that placing higher angular resolution onto a face improves eye tracking accuracy compared to a larger sensor. Thank you.
Great, and we have Brevin Tillman here to answer some questions. So go ahead and write any questions you have in the chat below. And I'll start off with a question from Huashan Tang. In the case of N targets, do you optimize the order of the targets somehow?
Yeah, so in the presentation, we show 2 Gaussians, but the way the algorithm works is you can just chain one region of interest to the next. So for N targets, it's just like in order. So we just chain to the next one as they come.
And I think the follow-on question is like, does the order matter, or is that like a user preference in terms of the scan path, like to go from top?
Yeah, so it doesn't matter because we start with 1 and that's kind of the anchor of the system. And then once you have 1, then you can go from there and update accordingly.
Great. So following on from that is like, so let's say you scale up to 2, 3 to more, and there must be a trade-off between the number of region of interest, like the total area of the region of interest, and the effectiveness of your method. Can you talk about that in a bit?
Yeah, like the bandwidth of the system suffering. Yeah, sure. So we've empirically tested this, and so let's say like for 2 targets in a scene, it's typically like 30 FPS, and if you add another one, it'll go down to like 20 or so. So there's definitely an increase as you add more targets, but we're going to explore this further in further work.
Okay. Takuya Funatomi has a question. How can we specify the targets to be tracked?
Yeah, so the most efficient way is to co-locate with a sensor. So say like a depth sensor or a thermal sensor that can give you the probability distributions right off the bat. In the paper, we start at a known initialization, but if you want to go off like an inference, obviously you could like pair it with a classifier and then use the bounding box as like the probability distribution or things like that. If that's what the question implies by specifying the target. But if you just want a general idea of where they are, you can co-locate with a sensor.
Great. Hisan says, great talk. What factors did you consider when you chose the MEMS mirror, like comparing a MEMS mirror versus like a fast tip tilt mirror or other kind of mirrors?
So I'll start with the advantage is typically speed. So really the main competitor to a MEMS mirror would be a Galvo mirror. And we're going to explore the trade-offs of the SNR because obviously Galvo mirrors are much larger than the small MEMS mirror we used. So we chose a MEMS mirror because it's one mirror. It comes with a controller, so we didn't have to design that in the lab. And it's very fast, so like 120 kilohertz. So it can multiplex the resolution extremely quickly.
Great. Let me see if there's any more questions. Maybe I'll ask one question. You mentioned that you can go to more number of targets and like with and possibly different types of distributions, not just the Gaussian. Does the math of the like explicit gradient calculation, do you have to rederive those for different distributions?
No, so the main thing is you just need a notion of where the things are in the scene. So whether you get that through any sensor, you can kind of enforce the Gaussians to be similar, right? Because if you put a bounding box around something, you use that to give you the variance of the Gaussians and things like this. So you would that's what you do in that
So
case.
okay, you'd use Gaussians. Okay. Well, yeah, thank you. So we'll continue on, but again, if you have more questions, you can put it in the live chat, and then Brevin and the other authors will answer at the end of the session. Continuing on, our next third talk is Deep Adaptive LiDAR, End-to-End Optimization of Sampling and Depth Completion at Low Sampling Rates. The authors are Alexander Bergman, David Lindell, and Gordon Whitestein, and we'll take it away.
Hi, I'm Alex Bergman, and I'm going to talk about Deep Adaptive LiDAR, End-to-End Optimization of Sampling and Depth Completion at Low Sampling Rates. Consider conventional LiDAR scanners. These scanners scan on a fixed grid and obtain depth at sampled locations by computing time of flight using a time-resolved photodetector. However, all of these scanning systems navigate a trade-off between range, resolution, and speed. In order to speed up depth image acquisition, we must either sample more sparsely, resulting in lower resolution depth images, or reduce the possible time of flight, resulting in shorter possible depth range. Complex processing algorithms on the sample depth can maximize this trade-off along a single axis, but are limited by the capability of the scanning LiDAR. However, emerging solid-state LiDAR systems, such as those based on an optical phased array, could allow for scanning of arbitrary patterns with no additional cost, breaking the trade-off. Thus arises the question of deciding how to optimally sample if we possessed such a system. In this talk, I'm going to show how we go from a single RGB image and a LiDAR with the ability to scan arbitrary patterns and produce a high-quality, dense depth image. We will take advantage of the capabilities of this LiDAR by predicting an optimized sampling pattern from the RGB image and using measurements at these samples to reconstruct the dense depth. We expect variations in the sampling pattern to have an effect on the quality of the reconstructed depth image, since these sampling patterns determine what real depth information we can capture from the scene. Methods such as uniform random and fixed grid samples serve as baseline sampling strategies, while Poisson disk samples generate random sampling patterns where the sampling points are spaced as far apart as possible. Other more complex heuristic methods, such as sampling near image gradients or placing samples on segmented objects in the scene, may make sense and improve performance depending on the reconstruction algorithm used. However, in this project we take an end-to-end deep learning approach to this problem. Specifically, from the RGB image, we parameterize a function with a deep neural network to predict an optimal sampling pattern and differentiably sample the depth values at these locations. Using the sparse depth image along with the RGB, we can introduce a second neural network which inpaints the missing depth values using information from the RGB image. Note that this architecture is fully differentiable and thus can be trained using only the loss between the ground truth depth and reconstructed depth. Before I get into detail on how we do this, let's summarize some related work. As mentioned, scanning LiDAR systems suffer from a trade-off between speed, resolution, and range. Adaptive scanning systems, such as those from Wang et al., attempt to address this trade-off, but don't optimize the scanning pattern with respect to reconstruction algorithm. On the other hand, monocular depth estimation approaches don't scan at all, producing outputs quickly using only RGB images. However, this is an ill-posed problem and these methods are not always accurate. Depth completion, the task of fusing sparse depth measurements with an RGB image, attempts to merge the benefits of monocular depth estimation with scanning LiDAR and optimize this trade-off between speed, resolution, and range. However, none of these methods include discussion on the sampling pattern, and thus we propose to generalize depth completion to also include optimal sampling pattern prediction. Our method has three main components: a sampling pattern prediction network, a differentiable sampling module, and a depth completion network. For the sampling pattern prediction network, we first use a pre-trained monocular depth estimation network to extract depth from the RGB image. This network removes RGB features which are not useful for predicting depth, increasing the performance of the sampling prediction network. Then, we use another U-Net convolutional neural network to extract a sampling importance vector field from the monocular depth estimate. This vector field intuitively has flow pointing into the regions where sampling at a higher density would yield a better depth estimate. In order to generate our sampling locations from this field, we initialize our samples in a grid on the image plane and integrate the field in order to determine the final locations for the sampled points. This is done because our experiments show that a grid sampling of depth produces high-quality results in the depth in painting task, and thus regularizing the norm of our vector field enforces grid-like sampling as a prior on our predicted sampling pattern. For differentiable sampling, we obtain the depth value of a sampled point using bilinear sampling kernels. To visualize this, consider the 4 pixels shown with depth values defined at their pixel centers. To sample location ij, we take the depth value of each of these 4 neighboring coordinates and weight by the L1 distance between ij and the pixel centers. This gives a differentiable relationship between the sampled depth value and the coordinate of the sampled point. We then arrange these samples in a sparse depth image. Note that we are still only differentiating through the sampled depth values, and thus there is a gradient mismatch between the sampled depth values and the sparse depth image. The last part of our end-to-end sampling and inpainting method is the depth completion network. Prior work has shown that convolutional neural networks do not perform well on sparse inputs. Thus, we broadly inpaint our sparse depth using a bilateral solver before feeding it and the monocular depth estimate into the depth completion network. We expect this to learn to preserve the low frequency depth scale from the inpainted sparse depth, but include high frequency depth features predicted in the monocular depth estimate. We can then apply a loss on the ground truth depth and to train end to end. Next, let's show some results. Here, we compare our adaptive sampling method to state-of-the-art depth completion networks at 50 samples per image. For a given RGBD image, we see that the results from sparse to dense, NCOM-CNN, and CSPN do not capture the high-frequency depth details and miss some objects when compared to our method. These qualitative examples verify this trend. Additional quantitative evaluation on the NYU Depth V2 test set confirms that our method outperforms all other methods at this low sampling rate. Similarly, we evaluate our adaptive sampling method on the KITTI depth completion benchmark and compare performance at 156 samples per image. For a given RGBD image, we see that the results from sparse to dense, NCOM-CNN, and sparse depth completion contain artifacts in the inpainted depth image when compared to our method. These qualitative examples verify this trend. Additional quantitative evaluation on the KITTI depth completion validation dataset confirms that our method outperforms all other methods at this low sampling rate. This system could be applied to autonomous vehicles in order to adaptively sample and reconstruct dense depth images with high fidelity at low sampling rates. This is shown here on the data from the KITTI Autonomous Depth Completion Benchmark. In the left column, RGB images and predicted sampling locations are displayed. In the right column, the reconstructed dense depth images are shown. Note that the predicted adaptive samples cluster in regions which appear to be distant from the camera. This makes sense as the loss we aim to minimize includes mean squared error in the depth domain, and thus accurately reconstructing distant regions is very important for minimizing this loss. However, due to the end-to-end differentiability of this system, it could be trained using a loss from higher level autonomous driving decision-making tasks, so long as they are differentiable. I'd like to thank my co-authors and collaborators, David Lindell and Gordon Vettstein, who have been amazing mentors. Thank you for coming to this presentation.
Ready.
And great. We have author Alex Bergman here with us. Again, if you have questions, I'll write it into the chat. And I'll start off with a question from Nick Antipa. He says, cool idea. Do you adaptively choose the number of samples, or is that a parameter that's fixed? And if so, how do you choose the number?
Yeah, so in this work, this is kind of a parameter that's fixed. And the way that we chose the number was we would just compare at different sampling rates and see at how low we could push the amount of samples and still achieve a depth reconstruction which is acceptable.
And just to follow up, empirically, what did you find? What's that like ratio?
Yeah. So I think in the paper we showed that for the kitty data set, it was about 156 samples per image, which comes down to about 0.1%. I would have to double check that number as I can't do the math in my head, but
okay.
Yeah, 0.1. Yeah.
Great. Ashwin has a question that there must be a lag between the RGB capture and LiDAR operation. He's curious if that's like modeled in the training and testing in any way, like that kind of like hardware, and if you can expect a loss in quality due to the motion of the system.
Yeah, so right now in this work, that was not modeled. Essentially, we just go from individual RGB frame to dense depth from that frame, and we assume that our LiDAR system would be able to capture depth from that original RGB frame. But if you, in reality, implemented this on an autonomous vehicle that was driving around, there would be such a lag, and kind of some future work could focus on overcoming this and modeling this into our system.
Great. Benjamin Attal has a question. Is it possible to use depth uncertainty rather than an initial monocular estimate of depth in order to choose sample points?
Yeah, I mean, I think that would be a reasonable way to go about this. I mean, as long as you have some information about where would be where it would be informative to focus more samples, I think this method could do fine. We used RGB images before, but we just found that the monocular depth estimate empirically worked a little bit better. So, but yeah, I think this would be a reasonable thing to use.
Great. Huashan wants to know whether this can work in real time or what frame rate the resampling works at.
Yeah. So I mean, so we don't have access to a solid state LiDAR, which is capable of actually scanning these points. So I think it would depend on the actual hardware that you use as to what frame rate this could work on. But yeah, so I don't really have a.
What about the back end, like the network? How fast does it take to the network?
Yeah, so the network, I mean, they're all relatively small neural networks. On our system, it would take about 11 milliseconds to do this processing task. So yeah.
Okay. Let me see if there's any other questions. Well, one last thing I wanted to ask is, you're doing this frame by frame, right? The RGB and stuff. If you wanted to do it for, like, let's say a video, like for moving LiDAR, like one of the main applications, how would you think, like optical flow or kind of flow temporal information, how could you incorporate that in, and how could that be useful?
Yeah, so I mean, I think exactly as you asked, the natural extension of this work would be to kind of incorporate multiple frames or kind of temporal information in order to possibly understand your scene more and be able to kind of continuously decide where to sample. So, I mean, something like optical flow could be used in order to sort of predict, you know, if you have one frame and you know where the objects are in that frame, and you have an estimate of optical flow, you could potentially figure out where those objects are going to be in your next frame and decide how to allocate your samples or reuse information from your previous prediction. So something like that would definitely be useful and a way to incorporate additional information.
Great. Well, that's all the time we have right now, but if you have more questions, again, add it to the chat and the authors will stick around. The last talk for this session is end-to-end video compressive sensing using Anderson accelerated unrolled networks. The authors are Yuqi Li, Miao Chi, Rahul Gove, Mian Wei, Roman Genov, Kyros Koutalakos, and Wolfgang Heydrich. And we'll start playing the video.
Hello everyone, my name is Yuqi Li. I'm going to present our work end-to-end video compressive sensing using Anderson accelerated unrolled network. This is a joint work of COS and the University of Toronto. Mask-based compressive sensing is a technique widely used in high frame rate imaging. By applying exposure control to each single pixel, we can encode the frames with a set of binary temporal masks and get the encoded capture images. The pipeline is formulated as a linear system, while X denotes the designed frames, Y denotes the capture images, Phi denotes the binary masks, and N denotes noise. The goal of the paper is using the masks and the captured images to reconstruct the frames. It is an air-conditioned inverse problem. Many approaches have been developed to solve it. There are a large number of model-based methods that use designed image priors for regularization, which can reduce the number of possible solutions and remove artifacts in frame reconstruction, such as total variation regularization, non-local low-rank constraint model, and the optical flow constraint model. Other methods such as Gaussian mixture model use the statistic of video to reconstruct frames. However, these methods are not suitable for all scenes. For example, total variation may create water wave-like artifacts. Non-local low rank may not work for unstructured scenes. Besides, they are all computationally expensive, especially compared to learning-based methods. The learning-based methods, including convolution neural networks and fully connected networks, have shown their efficiency and effectiveness in compressive imaging. However, they are inflexible to adapt to different masks. This brings challenge to jointly optimize full-resolution masks and reconstruction. The challenge is due to the huge searching space of masks, and the used reconstruction is inflexible to adapt to the change of masks. To deal with the problem, existing methods have to crop frames into small patches and optimize repeated small masks, but it may introduce structural artifacts. We found a solution that using unrolled network to jointly optimize full-resolution masks and reconstruction. Since our unrolled network is based on numerical optimization, I will start the proposed method by introducing the program formulation and the used optimization. The objective function consists of two terms. The first data fidelity terms guarantee a minimal resensing error, while the regularization term ensures that the reconstructed frame satisfies the desired prior model. Here we use JX to denote the denoising prior, which is weighted by parameter lambda. We adopt the half-quadratic splitting method to convert the problem into an unconstrained optimization problem involving variable x and auxiliary variable v. The problem can be solved by alternating optimizing the two subproblems with respect to v and x. In each iteration, we use a denoising CNN to optimize variable v and use a gradient descent method to optimize variable x. Here g denotes the gradient function and alpha denotes the step length. We can use Anderson acceleration to speed up the optimization. It uses the n previous iterations to compute a new iteration that converts faster to the fixed point. In Anderson acceleration, a quasi-Newton's method is applied to estimate root of the residual function, while in our method, we know the parameters from the unrolled network. We constructed the end-to-end network with architecture like this. The input of the network is the ground truth frames. We calculate the L2 loss between the ground truth and the output reconstructed frames to train the network. The overall network consists of a mask layer for generating masks and k stages for reconstruction. Each stage represents an iteration of optimization. First, let's take a look to the mask generation layer. A layer containing only bias values is constructed to generate the encoding masks. Since the masks used in high-frame-rate imaging are binary, we constrain that the output of the mask layer must be either 0 or 1 by using a sign binarization operation. This operation is inspired by the binary connect method. It is only activated during the forward and backward propagations but not during the parameter updates. Next, let's move on to the stage of the network. As mentioned before, the variable x in each stage is updated using a gradient descent operation, and the variable v is obtained using a CNN denoiser. Each stage acts as a residual block in the network. To improve the performance of the network, we change the update step of the variable x by adopting Anderson acceleration to the optimization. In Anderson acceleration method, the residue of each iteration will be stored and used in following iterations to speed up the optimization. To change the network to an Anderson accelerated one, we only need to add some skip connection to each stage of the network. These added skip connections change the previous ResNet into a more compact densenet. For the CNN denoiser in each stage, we use the architecture which consists of 2 residual blocks. Each includes 5 3x3 convolutional layers. Next, Miao will introduce the simulation and the experiments parts.
For training our network, we use 2 popular databases, the SubMeet database and the Sport Video in the Wind database. We randomly crop and select 3,000 video sequences to train our network, and select 800 video sequences of the same size for testing. In the simulation part, we use the compressive ratio 1:8. Here is the ablation study. We compare the performance of our model with and without the mask optimization and skip connection. The first row is the performance of only our reconstruction algorithm without our optimized mask. The second row is our reconstruction algorithm with our mask, but no skip connection. These 3 are the skip connection to 1, 2, 3 previous stage. We find the optimized mask can bring nearly 1.5 dB improvement in the PSNR, and the skip connection can bring nearly 1 dB improvement without increasing the number of parameters. The mask optimization and skip connection also shows acceleration on training. Here are the comparison of the mask used in our method and our optimized mask. After analyzing the spectrum distribution of these masks, our mask actually acts as a high-pass filter that blocks low-frequency spatial content. Then we evaluate our optimized mask by comparing it with random masks using the gap TV reconstruction method, which is only an optimization-based reconstruction method. Zoom in for detail of reconstructed results. We can see the image encoded by our mask are significantly better than those by random mask. Next, we compare our reconstruction method with other state-of-the-art method. Our method outperforms others by more than 2.2 dB in the PSNR. Here are the visualization of the reconstructed frames of different methods. Let us zoom in for the details. Here is the setup of our imaging system for the experiments and the imaging setting of the camera. We use the compressive ratio 1:22 in the experiments. Therefore, the reconstruct frame rate can reach nearly 1000 frames per second. The compressive camera we use in this paper is the 2-bucket camera. For traditional camera, the electron will only go to one bucket, or the capacity. However, the 2-bucket camera have 2 buckets. There is one bit switch which controls the electron to go to which bucket. By this, we can achieve different switch on and off on the different peaks. The 2 buckets masks are complementary. Therefore, theoretically, there is no light loss because of mask block. Here are the reconstruct results of the fans using different methods. For a fair comparison, the results are all reconstructed from one bucket encode images. The hardware we use is still a prototype, so the hardware itself will produce more noise than the commercial SDR camera, so that's part of the reason it looks so noisy. However, our work looks much better than the previous reconstruction method. Here is another example. Because of huge parameter of deep mask, their method can only do reconstruction patch by patch. There is some discontinuity between one patch and another. Maybe you cannot see it very clearly in this video. Please refer to our paper and supplementary material. Our model can handle the full image, so there is no such artifacts. To show the performance of the 2-bucket strategy, we compare the reconstruction result between using only 1-bucket data and 2-bucket data. We can see that 2-bucket data is more bright and less noise. This fan in this video rotates 2.5 rounds per second. And in this example, we increase the rotating speed of the fans to 7 rounds per second, where almost cannot see the edge of the fan in the captured image. However, it can be observed clearly in our reconstruction frames. Above all, in conclusion, we have proposed an end-to-end learning for compressive high frame rate imaging, which verifies the possibility of full resolution binary mask optimization. We show the equivalent between the Anderson acceleration and the dense network design. By adopting mask optimization and compact network, our method outperforms the state-of-the-art method by 2.2 dB. We also show our 2-bucket camera design can achieve both the high light throughput and high frame rate.
Okay, joining us now is Yuchi, who's going to be joining us by phone call. Please, write your questions in the live chat below, and I'll be monitoring that. So I guess I'll start off with a question, Yuchi, about the exposure time of your sensor with this coded bucket. Do you know what is the minimum exposure to actually have like a single, like one of those subframes, like not the entire frame, but like those subframes to realize a binary pattern?
The details of the camera, I think I'm not sure the number or the minimum number, but the camera can encode at least 100 subframes in one single encode image.
Okay, and that single encode image is probably like a normal exposure of a camera.
Yes. Yeah.
Okay. Yeah. Maybe the paper will have the details. And then the second question was kind of in the choice of the Anderson network. There's a parameter K. Is that fixed or chosen, or how do you choose that K parameter?
Actually, the K is the number of the stage of our reconstruction network. I guess you mean the M?
That's what I mean. Like that. How did you decide the number of stages?
The stage. Actually, there are trade-off choosing the number of stage. If you choose, for example, more than 50 stages, you may not be get much improvements, but you may cost some time and memories. In our paper, we use 40 near 40 stages, and we found both the speed of the reconstruction and the reconstruction quality are fine.
Okay. Let me see if there's any questions. If not, I'll ask a further question. So when you're doing this, like these patterns can either be one bucket or two bucket. You adapted, like the two bucket case, you have these kind of like complementary pairs, correct? In the mask?
Yes.
So is that explicitly designed into the network, or is that the network doesn't care about whether it's one bucket or two bucket, but then if you wanted to implement it on the hardware, the two bucket method would give you twice the amount of signal?
In the network, we can train the two bucket binary masks because our method is inflexible to the different masks. And if you use two buckets, that means you have two measurements. It doesn't matter. So I think there's no. We do it using the two bucket binary mask optimization.
Okay, so it is designed in. Okay.
Yeah.
Huazhan Tang has a question. Is there a reason the trained network takes a masked image as input versus the sum of the two bucket image? And so then it's not conditioned on the choice of mask?
I think we in our network we train the mask and the reconstruction at the same time.
Mm-hmm.
But I don't think the sum of the two buckets can have any advantages for reconstruction.
I guess I like following on. I think what they might be also asking, like, what if you like have the mask you actually choose is slightly different from what actually is implemented due to some error? Like, is your network robust to?
Yes. But the reconstruct quality may decrease little. But it's still robust because the network is flexible to adapt to different masks.
Okay, yeah, because if you had different hardware that maybe couldn't realize the masks, you don't have to necessarily retrain from scratch.
Yeah.
Okay, great. So that's actually going to end this technical session. So I want to thank the authors, and the authors will stay on for 4 to 5 minutes to answer questions in the live chat. Also, I want to remind the viewers that you can also asynchronously add comments to videos of all the technical sessions by going to the website and doing that, and those will be looked at. And finally, if you want to have a more informal, you can use the Slack to independently message authors. So with that, we're going to take to a virtual discussion break. Thank you for listening.